This episode is made in partnership with Cisco Global Problem Solvers, the series. This animated series features a team of teenagers tackling some of the world's toughest problems, like how to handle the aftermath of hurricanes. It aims to encourage 4th through 8th grade students to think of themselves as global citizens and to develop their problem-solving skills and use technology for social good. Click the link in the description to learn more. In August 1992, Hurricane Andrew flattened the Bahamas and smashed into the coast of Florida and Louisiana. Some 70,000 acres of trees were destroyed, and more than 250,000 people were left homeless. Hurricanes like Andrew are outliers, of course, but every year, similar powerful storms, from Katrina to Sandy, threaten communities around the world. And they're especially damaging to people living in poverty, as they often don't have the means to abandon everything when a storm's brewing or rebuild in the aftermath. Unfortunately, evidence is mounting that climate change could be making these storms even more violent. But what if there was a way to just make hurricanes go away? Or at least make them weaker? It sounds like science fiction, but hurricane prevention might be more possible than you think. First, though, let's get our terminology straight. The scientific term for these powerful storms is tropical cyclones. Hurricanes are tropical cyclones that happen in the Atlantic or the East Pacific Oceans. Typhoons are ones that happen in the northern West Pacific Ocean. Same physics, just different names depending on what continent they're hitting. How they form is not something that scientists totally understand, and what we do know isn't super straightforward. But they're sure that, by far, the most important factor is the temperature of the water at the ocean's surface. Cyclones can only form if that water is above 26.5 degrees Celsius or about 80 degrees Fahrenheit. Since water holds a lot of heat energy, that warm surface can heat up the air above it. And the simplified version of what happens from there is that this hot air rises. As it rises, it cools and condenses into powerful thunderclouds. Cooler air from elsewhere in the atmosphere then rushes in to fill the void left behind. It too heats up, and the cycle starts once again, eventually producing a mega-sized storm. In fact, hurricanes and typhoons are sometimes described as heat engines, since the process can be self-sustaining once it gets going. Well then, how do we prevent them? To stop an engine, you remove its fuel. So to stop a cyclone, you take away its warm water. One way we might do that is marine cloud brightening. Essentially, you fly airplanes above the tropical areas where hurricanes and typhoons form. Each plane sprays out a mist of seawater behind it, and those droplets, filled with little bits of salt, form nuclei for condensation of new cloud particles that can bulk up lighter, fluffier clouds. These denser, wider clouds reflect more sunlight back towards space. And with less light hitting the ocean surface, there'd be a smaller chance that the water reaches that critical 26.5 degree temperature needed for cyclone formation. A similar idea, called stratospheric aerosol injection, takes this principle and expands it to the whole planet. Instead of bulking up clouds one by one, special high-altitude planes could pump gases like sulfur dioxide into the upper atmosphere. That's a gas often released during volcanic eruptions, and it can be extremely effective at reflecting sunlight. We know this because major eruptions in the past have had measurable effects on global temperature and led to temporary reductions in tropical cyclones. After a 1912 eruption in Alaska, for instance, the world experienced the fewest hurricanes and typhoons ever recorded. Both of these ideas rely on nature doing our work for us, though. What if we acted more directly? That's where bubble curtains could come into play. A bubble curtain is made by injecting air bubbles deep underwater. As the bubbles rise to the surface, they form moving curtains which carry with them some of the deeper water. If this was done in areas where tropical cyclones often form, they could drag up cooler water to help lower the temperature at the surface. And again, no warm water, no cyclone. The neat thing is that unlike marine cloud brightening or stratospheric aerosol injection, this is already an established technology. In Norway, it's used in reverse, to bubble up warm water in the winter to clear ice from fjords. But even so, it isn't likely to be put into practice for hurricane prevention right away. You can lump the obstacles to all three of these measures into two main categories. The first is cost. Tropical cyclones form over huge regions of ocean, so we would have to deploy countermeasures in vast quantities. The U.S. National Oceanic and Atmospheric Administration estimates that to make a bubble curtain that effectively protects the U.S. Gulf Coast, it would need to extend over something like 850,000 square kilometers. And one study investigating global aerosol injection assumed we would need to disperse 5 million metric tons of sulfur dioxide per year. That could require tens of thousands of flights every year for decades just to slow the rate of increase in global temperature, let alone actually cool things down enough to prevent tropical cyclones. What's more, even a successful program would be wasteful because strong cyclones are the exception rather than the norm. I mean, of the around 80 tropical disturbances that form over the Atlantic Ocean in an average year, only 5 or so develop into storms that threaten the US. Maybe the bigger obstacle, though, is the collateral effects of large-scale action. Like, if we do manage to successfully change the water temperature across a huge swath of ocean, what does that mean for the ecosystems there? Given that the people most hard hit by tropical cyclones worldwide are also more likely to rely on marine protein sources, we'd want to be careful about doing anything that could negatively impact aquatic habitats. Similarly, while whitening clouds could meaningfully reduce the number of hurricanes and typhoons, there's also a significant chance it would dramatically affect other ecosystems. For instance, one study noted it'd likely reduce the amount of rainfall in the Amazon rainforest. And given what climate change is teaching us about our interconnected world, that kind of trade-off may not be worth making. So yeah, it might be possible to dissipate hurricanes, but we've got other safer ways to deal with the threats they pose, which are already at work. Like, we've gotten really good at predicting where those storms will go and bracing for their impact. That's already saving lives at a fraction of the cost. And if we can do an even better job of implementing forecasting technologies and helping those who are most affected by big storms, then completely preventing tropical cyclones won't be necessary. Thanks for watching this episode of SciShow. If you, or any kids in your life, like thinking about how to solve problems like this, you might be interested in today's sponsor. Cisco Global Problem Solvers, the series, aims to inspire 4th through 8th grade students to become, well, global problem solvers. It encourages them to think of themselves as global citizens, developing skills like critical thinking and teamwork. In Season 2, learn how the team uses business skills and tech to get students back to learning after a hurricane hits the US Gulf Coast. If you want to check it out, we've linked to the series here. And if you're interested, you can also access teacher's guides with discussion topics and worksheets by clicking the link in the description.